All right, this is an explanation, not to Gary. He can't be explained to. I mean, we've come full circle around to the very first thing he ever blocked me about with this relative velocity and blah, blah, blah. But just in case anybody else is interested. Okay, here we have a little diagram. Here's you in this platform. We're going to talk mostly about the reference frame. This is our primary reference frame. Okay, but we'll talk a little bit about the ship. Here's your ship with a little tiny guy in it. And it's traveling half the speed of light relative to this guy. So it's going this way, half the speed of light. And it fires off a photon. That's this little wiggly line. And I'm just showing, and it shoots out at the speed of light. This guy sees the photon going speed of light. And then this ship over here, it's going half the speed of light. So, yeah, to this guy, it's going half the speed of light relative to this guy's platform in space. Right? So this guy actually sees the light shooting away, used loosely, meaning if you measured this light speed, say there was more than one photon and you took some of them to measure the speed or whatever. You know what I mean. It's going light speed, and this guy's going half the speed of light, so it actually does look to this guy like that photon is moving away from this ship at half the speed of light. Yeah. So the weird thing comes, though, with this guy. What Einstein is claiming is that this guy also sees that photon shooting out at the full speed of light. Now, this guy's coasting, at this half speed of light. So he doesn't think he's moving. He doesn't sense any problems. He just sees that photon shoot off at the speed of light, and he's at rest. So how could that be? How could this guy see this go off at the speed of light, and this guy sees that relative to the ship, it's going half the speed of light, like Gary would like. Gary would like to think that this guy will see it go at half the speed of light. Well, no, that's not possible now, because it's just the elements of this have been checked. There might be different explanations, but mathematically, no. But anyway, sorry, back to how this could be. And Gary is very much like, how could that possibly? Well, that's where the time dilation comes in. You see, if this guy over here sees this guy's time is going slow, right? This guy's time is going slow. So a photon shooting out at half the speed of light to this guy's time is slowed down, right? If this time is slowed down half, then that photon going half as far does it twice as fast, right? Because this guy's slowed down, everything else seems faster. That's why there's the time dilation was predicted, because there would have to be a time dilation for this to be possible. For the Michelson-Morley experiment to be true, and the light is always going at the speed of light no matter what, then this guy's time would have to slow down. But it's not really as simple as that, because the length also contracts and the mass dilates. And so the wavelength of this photon changes. And as a matter of fact, it changes exactly right with the spreading of space, stretching out the wavelength, the amount of energy, which E equals mc squared. A photon has a rest mass, which is the amount of mass it would be if turned into matter, E equals mc squared. All of those things dilate and contract together, making the answer work out right mathematically. Right? So the answer to how come you could shoot something and this guy, where Gary's brain is, sees the photon going out at half the speed of light relative to your ship, registered back to the ship, he also sees your clock going slower. So you see the photon, and because your clock is slower, the photon seems to be going faster again to you. So the same photon going through space at the same point The difference in speed has to do with your clock speed. And that's what Einstein, how he said it worked. And Hythloday showed a video about how the bending light around other gravitational bodies has been done many times. And you obviously don't know what diffraction is. You're talking about scattering. You're talking about... I don't take your theory seriously because it makes no sense. But also, maybe that's because I've worked in science and done the math, and it's like you have to reproduce the math, or you have to fill in a philosophy that matches the math, because this theory that they've never put light through a slit or two slits, and they build lasers so well they can make them cheap and predict how to make a laser disc reader and stuff because they're so good with the optics. And lasers are using the quantum effects to achieve these great things that lasers do for us. And I told you, MIT, you went to MIT, you should have done the problems in the coursework, not just watch the videos. And there's software, MEEP, MEEP, from MIT that simulates this and actually any optical thing using the Maxwell equations and the appropriate, quantum mechanical factors well enough to simulate and then build an optical bench, a device, and it behaves the way expected. No, not perfectly, because it's doing a perfect simulation and you might have a screw cranked a little bit too hard. It's you that's not perfectly matching the math. And plus, these experiments have been done for 100 years, and with the Galilean relativity 400. And when you say it's weakly evidence, you should always be admitting it's because you reject the results. Not because they never occurred, right? Because you reject the results and say everything left isn't conclusive, that wouldn't be a lie. But saying it's never even been done, that's a lie, right? Your other side of your coin is that you think all of these scientists have been lying, and that's just not the kind of problem you have in science. You have to be able to prove what you say in a lab in physics. Measurable. And what you should do, I'm going to suggest now to Gary, I am talking to Gary now, obviously, because I have a suggestion. You figured out that a laser, according to your system, a laser at speed will not come out straight. Like a hose, it'll bend back, right? And and maybe your laser even, you don't know, maybe it's a problem with the laser. Well, you turn the laser over the other way, where you're spinning around the world in a different direction, relative to the laser, and see if it bends the same or a different way. Right? Because you're on the Earth and you're traveling 1,000 miles an hour or something. Right? So you could detect that. And the lasers they have in regular labs, well, if you could point it one way and point it back, and you'd see, they're delicate enough to see the redshift. And you're just a fool to think that none of these people that like playing with lasers will be bothered to actually check this stuff because they know it's not true. And the amount you're demanding being spoon-fed and then saying, we're just rude to you. Not you, though. You haven't noticed you're rude. Anyway.